No matter how good a stick snapper is, if it picks up a metal rod instead of a stick, well, it's not going to be able to snap that. And if you put some braces on its wrists, it's not going to be able to snap things either. These are like our competitive and our non-competitive and uncompetitive inhibitors. So competitive inhibitors bind to the active site, so they mimic the substrate and bind in its place. So that's like our metal rod. Whereas we also have other types of inhibitors which bind elsewhere on the protein. So those are going to be like our wrist braces, and so they're binding not at the active site, but somewhere else and preventing the enzyme from doing its job. There are different types of these inhibitors that bind elsewhere. And so we'll talk about non-competitive, uncompetitive, and mixed. And those terms refer to whether they're binding to the enzyme alone or to the enzyme substrate complex. Depending on the type of the inhibitor, we're going to see different effects on the apparent activity of the enzyme. So we might see a difference in the apparent Km. So remember, our Km was a sort of measure of affinity. We might see differences in our Vmax, so the actual amount of activity that we're seeing. These are apparent differences, and because the enzyme, it's not like it's actually likes its substrate less if it has the presence of an inhibitor, but you can be tricked into thinking that if an inhibitor is present. And so we see differences in the apparent constants for our kinetic constants, but not the actual underlying constants. And when these inhibitors are removed, the enzymes are going to act normally. And so we'll talk about this, but just keep in mind that we're not changing the enzyme itself permanently in the case of these reversible inhibitors. We will talk about one type of inhibitor, a covalent inhibitor, or sometimes these are called mechanism-based or suicide inhibitors. These are more like mousetraps. And so the enzyme goes to pick up a stick, and it looks like a stick, but it's really a mousetrap or one of those finger traps or something. And so the enzyme gets permanently incapacitated, and therefore it's going to act a lot differently than these other reversible types of inhibition. And so we're going to focus mostly on the reversible inhibition, but we will talk about the covalent inhibitors. An example of this would be like penicillin or beta-lactam antibiotics that actually bind to the enzyme and actually kind of trick it into attacking it. And in this cases, it's going to get permanently stuck. And so that would just kind of permanently incapacitate your enzyme. Whereas competitive inhibitors can be competed out. So let's dive in and talk more about what differentiates a competitive, a non-competitive, an uncompetitive, and a mixed inhibitor, as well as what these covalent inhibitors are. So remember, substrates are the reactants for an enzyme catalyzed reaction, and the enzyme is going to bind to those substrates in the active site, do that whole induced fit to get them into that transition state, and then release the products. And it's that transition state that the enzyme makes the most comfy contacts with, because the transition state is the most unstable part of the transition from substrate to products. And by forming these favorable interactions with that transition state, the enzyme is thereby able to lower the activation barrier, the energy needed to get to that transition state. And thereby, the enzyme is going to make it faster for this reaction to happen. But that can only happen if it's actually picking up a substrate and if it doesn't have something bound elsewhere that is going to be preventing it from converting that substrate into product. So in the active site, that is where your substrate is going to bind, and that is where some of our inhibitors are going to bind. So that would be our competitive inhibitor and our irreversible inhibitors typically. They bind in that active site, and they typically mimic the substrate. So they're typically going to look like the substrate. And although I'm talking about substrate, typically if you want a really strong competitor, you're going to want to mimic the transition state. We call these orthosteric inhibitors when they're binding to the same place as the substrate binds. So they're binding in the active site. We call them orthosteric. We also have inhibitors that bind elsewhere. We call these allosteric inhibitors. So other, remember we talked about allosteric effects where something happens in one place in the protein that affects other things that are happening elsewhere in the protein. We talked about allosteric effects when we talked about hemoglobin and how a modulator binding to one side of hemoglobin affected something happening elsewhere on hemoglobin. Similarly, our allosteric inhibitors are going to bind elsewhere on the enzyme, so not in that active site, but somewhere else, and change the shape typically of that active site, make some sort of conformational change that is going to hinder the enzyme from doing its job. And so You are not competing for the actual site in the case of the allosteric inhibitors. You're just making it so that the enzyme can't actually use the substrate, even if it can pick up the substrate. So remember that our enzyme catalyzed reactions, we have the binding steps are going to be reversible. And so the binding of some of these inhibitors is also going to be reversible. And when you have reversible binding, we can take advantage of that to sneak inhibitor in or sneak substrate in or dilute the inhibitor out if you allow the enzyme to drop it. And so we'll talk more about this when it comes to how we can overcome these inhibitors by diluting or by competing. But remember, this is a reversible binding enzyme plus substrate. You get the enzyme substrate complex. You get that induced fit through that transition state into enzyme product and let it go and do it again and again. The inhibitors are either going to bind in the place of the substrate, so our competitive inhibitor, they're going to bind in the place of the substrate and get stuck. Our case of our irreversible inhibitor, our covalent inhibitor, mechanism-based, suicide inhibitors, lots of different words. These are going to mimic the substrate too, bind to that active site, prevent the enzyme from doing its job. And so those can only bind the enzyme, not the enzyme substrate complex, because they're physically competing for the same site as the substrate. So competitive and irreversible inhibitors are going to mimic the substrate typically. So they look like the substrate. They look like a stick, but they're really a metal rod, or they're one of those finger trap sticks, and they bind on to the enzyme in that active site. We call these orthosteric. So our competitive and our irreversible inhibitors are only going to bind to E. They're only going to bind to that enzyme alone. They cannot bind to the enzyme substrate complex or the enzyme product complex because they're binding to that same location, that same active site. Our allosteric inhibitors are non-competitive, our uncompetitive, and our mixed inhibitors. These are going to bind elsewhere. Because they're not competing for that active site, they can bind elsewhere on the protein. They are going to be able to bind to the enzyme substrate complex, and sometimes they bind more to the enzyme substrate complex, and sometimes they bind more to the enzyme alone. And depend on what kind of they prefer, we can give them different names: non-competitive, uncompetitive, or mixed inhibitors. All of those are examples of our allosteric inhibitors, and we're going to go into more detail about each of these. But a non-competitive inhibitor is going to bind to E or ES equally well. And this is actually a special form of what we call mixed inhibition. And so in mixed inhibition, it'll bind to E and to ES, just like in non-competitive, because non-competitive is a form of mixed inhibition. But in the case of our non-competitive inhibitors, they bind equally well to the enzyme alone or to the enzyme substrate complex. They're like the you do you, I'll do me, I'll bind wherever I want, E or ES, equally well. Whereas our uncompetitive inhibitors, these bind to ES, but not E. And so they bind to that enzyme substrate complex, but not to the enzyme alone. And so often what happens is that when the enzyme binds to a substrate, it has some sort of conformational change or somehow opens up a site that the inhibitor can bind to. So that inhibitor is binding to the enzyme substrate complex, but not to the enzyme alone. Typically, what you have is some form of more mixed situation where it binds to E and to ES, but with different affinities. But unlike competitive inhibitors, they can bind to ES. They just bind to different amounts. Whereas the competitive inhibitors cannot bind to ES because they're binding to that site where the S binds. And so it's only going to bind to the free enzyme. It's going to do this reversibly, but the irreversible inhibitor is going to do that irreversibly. The non-competitive, uncompetitive, mixed inhibitors, they can bind to ES, and some of them also bind to E. And we'll get into all of these. I'm also not going to get more into here. There's this thing called reversible covalent inhibition. They form bonds at that active site, but they're typically to a sulfur or something, and so they're going to be reversible, but they are covalent, so they're stronger than the competitive, but they can be overcome. And so this is a way that you limit off-target activity, but not going to go into that here. If anyone's interested, I have a video on that and things. But for now, we're just going to focus on kind of these simpler cases. So we have these types of inhibition we'll talk about: competitive, irreversible, non-competitive, and uncompetitive. And remember that mixed is just a type of non-competitive where you have unequal affinities for your enzyme and your enzyme substrate complex. How can we overcome this inhibition? It depends on the type of inhibitor. So for some inhibitors, we can compete them out Whereas for some of them, we can dilute them out or compete them out. And for some of them, we can't do any of those. So let's go through what I mean by compete out and dilute out. So when I talk about competing out, this is saying that I'm adding a bunch of the actual substrate to kind of flood out the fake substrate, that inhibitor. And this only works, however, if the inhibitor and the substrate are binding to the same location. So now when that enzyme goes and it drops that inhibitor, it is likely to find substrate and not inhibitor. And so you're able to compete out the inhibitor by adding increased concentrations of the actual substrate so that when your stick snapper drops that metal rod, it picks up a stick and not another metal rod. And so this only though works if they're binding to that same site. So this is only going to work in the case of competitive inhibition. Don't worry if you have another type. So maybe you've got uncompetitive or non-competitive or mixed. What all of those have in common is that they bind to somewhere other than that active site. And so we can't just compete them out because it doesn't matter how much of that actual substrate is around, we're still going to be binding to that enzyme substrate complex. So instead, what we need to do is make it so that there's just less of the inhibitor around. And the way that we can do this is by diluting out the inhibitor. So do something like change out the buffer or otherwise remove that inhibitor so that when the enzyme drops the inhibitor, and so remember those are just our non-covalent interactions. And so you've got binding and unbinding and binding and unbinding. And when you have one of those unbindings, well, now there's not any inhibitor around in order to bump into and bind to again. And so now that enzyme is able to do its catalysis. And so maybe it already even had a substrate in hand. It just couldn't do anything with it because it had its hands tied by that inhibitor that was binding elsewhere. And now, in the absence of that inhibitor, the enzyme can do its normal thing. And so you can dilute out if you have an uncompetitive, non-competitive, mixed inhibition, or even if you have a competitive, because we are physically removing the inhibitor in this case, as opposed to just kind of overwhelming it with the actual substrate. So it's more likely to bump into a substrate in the case of competing it out. Here, we're actually like physically removing that inhibitor by diluting it out. And so taking advantage of those non-covalent interactions and the fact that the enzyme, if it dissociates from that inhibitor, it's got to find another copy of that inhibitor in order to pick it back up, or that same copy, but if it's like floating around from fusion and things, if you have less of the inhibitor present, then you're not going to be able to be inhibited. And so take it all the way down to zero inhibitor, and well, there's no inhibitor to inhibit you, and the enzyme goes about its business. This also helps us see that we really are just seeing apparent changes in that Km and that Vmax when we have an inhibitor present, because when we remove that inhibitor, the enzymes should be like completely back to normal in the case of any of these non-covalent inhibitors. So our competitive, uncompetitive, non-competitive, or mixed inhibitors. In their presence, we see differences in the Km apparent and the Vmax apparent, but those differences are not actually affecting the enzyme's actual goodness at doing its job if you take away the inhibitor. When you take off the handcuffs, it's still able to function just normally. This is not the case with one of our covalent or mechanism-based or suicide inhibitors. Remember, those are more like our mouse traps, so the enzyme kind of goes to bind it and it gets stuck on that inhibitor, and then the inhibitor is actually making it so that the enzyme can't do anything, and it's stuck with the covalent bond that it's not just going to fall off. So remember that diluting out and competing out, we're relying on the non-covalent interactions and the fact that the enzyme would eventually drop that inhibitor. But in the case of our covalent inhibitors, the enzyme is not going to drop that inhibitor. And so we can't dilute it out or compete it out because it's stuck on there. So with those covalent inhibitors, we're not going to be able to dilute out or compete out. Our only hope is kind of just waiting for the cells to make more of the enzyme and removing that inhibitor so that the new enzyme that is made doesn't get inhibited. We have our competitive can be overcome by diluting out or competing out. Non-competitive can be overcome by diluting out, uncompetitive can be overcome by diluting out, and mixed can be overcome by diluting out. But these cannot be competed out, at least not fully. So if you have an inhibitor, say that binds to the enzyme more than the enzyme substrate complex, then you can kind of maybe reduce the effects of the inhibitor by competing it out. But at least for the sake of this class, we're just going to consider that the only one we can compete out is the pure competitive inhibitor. And then the other non-covalent ones we can dilute out, but our covalent inhibitors we cannot compete out or dilute out. So this is just kind of like an introduction to these terms, and now let's go and dive into their details and what type of evidence they leave in the kinetic data. But they're irreversible or covalent inhibitors that are binding to the active site and basically keeping the enzyme from doing its thing. Typically, you're going to see this with an enzyme that has a covalent catalysis mechanism. As for what it's going to do with the kinetics, we're not going to bother with that. So you're going to have a decrease in activity of your enzyme. The effects with KM can be a little strange to think about because it gets all really technical and weird. And typically when you're dealing with these curves and stuff, and you're talking about the effects on KM and Vmax, you're typically dealing with these with reversible inhibitors, and that's going to be our focus. So when we talk about our reversible inhibitors, remember we can have our orthosteric and our allosteric. Our orthosteric inhibitors, these are going to be binding in the active site, and these are typically going to be our competitive inhibitors. Whereas our other types of inhibitors are going to bind in an allosteric site. So remember that if you're able to bind to the enzyme when it's bound to the substrate, you've got to be binding somewhere other than just the active site. So if you think about what these might look like, well, a competitive inhibitor, one of those orthosteric inhibitors, is going to look like your substrate or your transition state. Whereas one of those other forms of inhibitors, those allosteric inhibitors, it can look like pretty much anything. You can't really predict what it'll look like because they can bind to various places, and you never know like where binding at one thing will influence the shape of another site and things like this. So let's now look at how these influence our kinetics. So first, let's just review our Michaelis-Menten kinetics. So we basically have the situation where the enzyme binds to the substrate, and then it can bind and unbind and bind and unbind and bind and unbind, and those are given with rate constants of K on and K off. Once it's bound, you have this enzyme substrate complex that can then go and get catalyzed, converted that substrate into product, and this is given by our kcat. So the kcat is going to be the rate constant for that turnover, and we call this kcat therefore the turnover number. So that's telling you about like a single enzyme doing its best, how fast can it go? Km, this is going to take into account basically how much of this enzyme substrate complex we have, which is going to depend on how much you like the substrate, how tightly you bind, as well as also a contribution of the kcat, because, well, how well you turn into product, that's also going to influence how much ES you have. Roughly a measure of infinity, we have this Km, because the larger the concentration of substrate you need in order to get the same amount of basically productive product form is going to tell you that, like, well, if you need more substrate, you're not binding it as well probably. And so we say that the Km is a measure of binding affinity, where the lower the Km, the higher the affinity. And we can figure this all out experimentally by measuring the rate at which product is formed over time in different substrate concentrations, taking the slope of the linear portion, this V naught, and then plotting those out and finding the concentration of substrate at which we got our maximum velocity and our half maximum velocity. We can get the kcat from dividing the maximum velocity by our enzyme concentration, and we can get the Km by taking the concentration of the substrate that got us to half of that value. So this is going to be the basics of Michaelis-Menten kinetics. Now let's go and look at how these kinetics are going to be influenced by our inhibitors. So a competitive inhibitor is competing with the enzyme for that active site. It can only bind the enzyme when it's alone, because, well, if the substrate's there, there's no room. So it's going to bind to the enzyme site. It usually is going to mimic the substrate and bind in the same place. Now, the enzyme, it has a choice. Is it going to bind the inhibitor or is it going to bind the substrate? Well, it's going to depend on its relative affinities for the two and the concentrations of each of them. If you don't have any inhibitor present, well, then that would be your normal Km. But what if you start introducing inhibitor? Well, now you're going to have more of your actual substrate in order to get to your half maximum velocity. And so it's going to look like you have an increased apparent Km. It's going to look like you have a worse affinity because it's going to take you more of the real substrate in order to get to that maximum velocity. But that maximum velocity itself is going to be the same because, well, if you add enough of the substrate, you're basically diluting out the inhibitor to such a degree that as long as the inhibitor is not permanently stuck on there, if it just like happens because to unbind, well, now the first thing it's going to pick up is going to be a substrate. It's more likely to pick up a substrate than it would be to pick up an inhibitor. So remember that you have this binding and this binding and this unbinding of the inhibitor, not just of the enzyme and the substrate. And so you have to think about, okay, well, if the enzyme were to drop the inhibitor, would it be more likely to find another copy of the inhibitor or a copy of the substrate? If it's more likely to find a copy of the substrate, and if it has a higher affinity for the substrate and things like this, well, then you're more likely to find it bound to the substrate than bound to the inhibitor. And so that's why you can compete these out and reach the same Vmax. However, the amount of the substrate that's going to take you to get to the Vmax and to the half Vmax, that's going to increase. So remember that it's not the actual Km that's going to be changing, but the apparent Km is going to be changing because the real substrate is being diluted out. But we can dilute the fake substrate out as well by adding more of the real substrate. Non-competitive inhibitor. So here, it's like you have less enzyme. And so if we think about why this is, well, it's because the inhibitor is binding it and keeping it from doing what it's doing. And the way that we measure how much enzyme we have, well, I mean, like the way that we measure enzyme activity or whatever, we're measuring its activity. We're measuring the formation of product. And if we're saying that the enzyme can't do that, it can't form product, then it's going to look like there's not as much enzyme there. And so remember that the non-competitive inhibitor, we're binding to the enzyme at an allosteric site, so someplace other than the active site, and we're somehow incapacitating the enzyme, keeping it from doing its job, keeping it from converting the substrate into the product. So remember that purely non-competitive inhibitor is going to be able to bind to both the enzyme alone and to the enzyme substrate complex with equal affinities. So it doesn't care. It's not competitive with that enzyme for the substrate. It's not competing with that substrate. It's saying you do you, I'll do me. I'm going to bind the enzyme over here. Go about your business. And so if it's doing this, well, what's that going to do? It's going to make it seem like we have less of our enzyme. If we have less of our enzyme, so remember our Vmax, that was going to come from our kcat times our enzyme concentration. If we're saying it's like we have less of our enzyme, so we're going to get a decrease in our apparent Vmax. What about our Km? So remember, if we can simplistically think about Km as a measure of binding affinity. If this non-competitive inhibitor is not competing, well, then it's not going to change the affinity of the enzyme for the substrate. And so the apparent Km is not going to change. And so that's why we have, in this case of a purely non-competitive inhibitor, we have no change in the apparent Km, but we do have a change in the Vmax, the apparent Vmax. Because the competitor binds in a different location, it's not competing, but it is keeping the enzyme from doing its job if the enzyme does bind to that substrate. Often what we're going to see, though, is mixed inhibition, where there are different affinities for the E and the ES. So non-competitive is just a special case of mixed inhibition. With mixed inhibition, you're still going to get that lower Vmax, but your Km can either go up or it can go down. It's a little confusing, but hopefully it'll make a little more sense once we talk about the uncompetitive inhibitors. But basically, you can think about, if it's preferring one form over the other, like if it's preferring the enzyme alone form, well, then it would be kind of like drawing this and pulling your reaction this way and making it seem like your enzyme had worse binding. So that would be kind of like your competitive inhibitor, which was going to increase your apparent Km. Well, if it was binding to this enzyme substrate complex better, well, this would actually make it look like it had tighter binding, because if you think about Le Chatelier's, you're pulling things this way, you're going to have increased binding. It'll look like you have increased binding affinity. You're going to decrease your apparent Km, that is, increase your apparent affinity. So hopefully it'll make a little more sense once we talk about uncompetitive inhibition. So remember your uncompetitive inhibitors, that's where you're binding to the enzyme substrate complex, but not to the enzyme alone, and you're preventing the substrate from being converted into product. So when the enzyme binds to the substrate, now you might have like a little site open up or something. That's going to allow the inhibitor to bind, and once the inhibitor binds, it's going to be incapacitating it. So if you think about our types of inhibitors, if you think about kind of the competitive inhibitor, that's going to be like your fake stick. If you think about a mixed inhibitor or a non-competitive inhibitor, that can be kind of like you're grabbing onto the stick snapper's wrist. but just kind of in either way. And so the stick snapper can still grab onto a stick, but it can't do that kind of like movement of its wrists in order to snap the stick. What you're saying when you're saying it'll only bind to the enzyme substrate complex, like the case of uncompetitive inhibitor, is maybe only when you're in that form that's bound to the substrate, only then are you going to grab onto their hands and keep them from doing what they want to do. So because you're keeping the enzyme from doing what the enzyme does, you're going to decrease your apparent Vmax. However, you're going to get kind of a weird result with your Km. Because what you're going to be doing is you're going to be drawing the enzyme substrate complex like to the right. Good old Le Chatelier's, you're drawing things this, it's going to look like you're increasing the affinity of the enzyme for the substrate because you're going to be kind of like pulling it out here. And if we're saying that you're increasing the apparent affinity, what that means is that you're going to be decreasing your apparent Km. So it's going to take less of the same amount of substrate in order to get to your half maximal velocity, but the half maximal velocity is going to decrease. And so your enzyme to substrate complex becomes stabilized, but they're kind of useless. So to summarize, we have this enzyme bind to the substrate. We get this enzyme substrate complex that gets converted into the enzyme end product. So remember, we kind of lump together the forming the product and releasing the product, and we say that that's kind of like our kcat. And then the binding to the substrate, that's kind of like our Km, but the Km also takes into account this part. So it's not as simple as saying binding affinity, but it's often just considered a measure of binding affinity. So similar to KD, and that the lower the better, but there is that extra complicating factor, and so not completely affinity, but we can approximate affinity. And now let's say we have an inhibitor. We have a competitive inhibitor. It's going to bind to the enzyme and alone. It's going to prevent the enzyme from getting to the enzyme substrate complex. Well, what this is going to do is if the enzyme can't get to that, you're going to need more of it. You can compete it out because the enzyme isn't prevented from doing its business. If it actually binds the substrate, it can still snap it. But it's like the stick snapper keeps finding these fake sticks. So we can compete it out. If we add enough of the real sticks, we can kind of make it so that when the stick snapper drops that stick, it can find another one, it can pick it up and keep snapping. And so because remember on our catalysis Mending curve, we have like substrate on the x-axis. If we have enough of that substrate, we can finally compete out the inhibitor. And so we're going to get this to the same Vmax, but we will take us more of our substrate to get there. So it's like we have a lower affinity. That is, we have an increased apparent Km. So a competitive inhibitor, we can compete it out with substrate. With our other types of inhibitors, we cannot compete them out with substrate. And if we can't compete them out with substrate, that basically means we're going to take some of our enzyme out of commission. And if we take some of our enzyme out of commission, well, then we're going to decrease our apparent Vmax. What might change is our Km. And it could go up or down depending on our type of inhibitor. If we have a non-competitive inhibitor, what this is saying is if it's purely non-competitive, it's going to bind to the enzyme alone or to the enzyme substrate complex. Because it can bind each of these equally well, then it's not going to change the apparent affinity of the enzyme for the substrate. You do you, I'll do me, I'm binding over here, I don't care what you're doing. So that's going to be your non-competitive inhibitor. So that's not going to change your apparent Km, but you will have that decreased Vmax. With mixed inhibition, you're going to have non-equal affinities to the enzyme alone and the enzyme substrate complex. Then things can get a little complicated. And so the Km could go up or down, depending on whether it acts more competitive or more uncompetitive. So with an uncompetitive inhibitor, remember here, we're binding only to the enzyme once it's bound to the substrate. And once the enzyme is bound to the substrate, the inhibitor binds and prevents the substrate from being converted into product. What this is going to do is it's actually going to pull the reaction this way. You're stabilizing that enzyme substrate bound form. You're pulling the reaction this way. You're going to make it seem like it has a higher affinity. You're going to decrease the apparent Km. But you're still going to get that decrease in your Vmax that you measure. So with these non-competitive and uncompetitive inhibitors, you cannot compete them out, but you can dilute them out. So when we say compete them out, that's like we're adding more substrate and we can get to the same Vmax. And the only time we can do that is if we have a competitive inhibitor. But we can dilute them out, where basically if we're diluting them out, that basically means we just kind of wash them out. so that if the enzyme can't find an inhibitor to bind, well, then it's not going to be bound. You can't compete these out because, well, they're not competing for the same site. So even if you add a bunch more substrate, the substrate binding wasn't the problem. The substrate has plenty of sites to bind, and the inhibitor is not preventing that. If you want to keep the enzyme from binding the inhibitor, you have to make it so that there's like less of the inhibitor. So to summarize, competitive is going to bind to the enzyme alone. It's not going to change our Vmax apparent, but it's going to increase our Km apparent. Our non-competitive, this is going to bind to E and ES with equal affinity. It's going to take that enzyme out of commission. That's going to decrease our Vmax apparent. But if you're binding to E and ES with equal affinity, that's not going to change your Km apparent. Uncompetitive, here you're binding to ES and only ES. That's going to decrease your Vmax apparent. Remember, you're taking the enzyme out of commission. And then that's going to do, though, is it's going to basically stabilize that substrate bound form. It's going to pull the reaction towards the enzyme substrate complex. That's going to decrease your apparent Km, make it look like you have a higher affinity. Mixed inhibition. Here you're binding to E and to ES, but with different affinities. Once again, you're taking the enzyme out of commission, decreasing your Vmax apparent. But because you have different affinities, this may increase or decrease your Km apparent. If it acts more like a competitive inhibitor, binding to the enzyme alone tighter, well, that's going to increase your apparent Km, just like you had with your competitive inhibitor. But if it acts more like an uncompetitive inhibitor, well, then it's binding to the enzyme substrate complex more, and that's going to decrease your apparent Km. So you can't really tell, it's hard to tell based on a graph or something like that, whether something's mixed. Mixed is actually a very common form of inhibition. Now remember, all of these are changing what you're measuring, so they're changing the apparent things, but they're not changing the actual kinetic constants, the actual Km, the actual kcat. They're just changing kind of what you are measuring. And in the case of our competitive inhibitor, we can compete or dilute it out. And in the case of our non-competitive, uncompetitive, or mixed inhibitors, we can dilute them out, but not compete them out. And in the case of our covalent competitor, or our irreversible inhibitors, we can't do any of those. The only way to kind of get activity again would be to add more enzyme. Often when you're talking about trying to figure out what type of inhibition thing is, you might use a Lineweaver-Burke plot. This makes it easier to kind of see the differences in these key values fairly quickly, but use caution with Lineweaver-Burke plots because of the whole deal where the points derived from the origin, where you have a really low substrate concentration and your data is probably not that accurate anyway, are going to have a kind of like lever effect where they're going to pull the data, pull the slope, and greatly influence the values. But remember that with a Lineweaver-Burke plot, you have 1 over S on your x-axis and 1 over V on your y-axis instead of S over V. Then your minus 1 over Km is going to be your x-intercept, and 1 over Vmax is going to be your y-intercept. So if your apparent Vmax gets smaller, what's going to happen is that this is going to get shifted up. And if your Km or your apparent Km gets bigger, then what's going to happen is that this is going to get smaller. So if we have competitive inhibition, remember that's going to increase our Km. So in the presence of our inhibitor, if the Km was getting bigger, this is going to get smaller, it's going to get closer to the origin. And we're not having a difference in our Vmax, so we're going to have the same y-intercept. In the case of uncompetitive, so remember that was going to decrease our Km, so that's going to shift our y-intercept out here. And it's going to decrease your apparent Vmax, and so that's going to increase this intercept. And in the case of our non-competitive, which remember is a form of mixed inhibition, in the purely non-competitive form, you're going to have your Km unaffected, and so your x-intercept is going to be unchanged. But because your apparent Vmax is going to be reduced, what's going to happen is that, once again, you're going to see that with the inhibitor, you're going to be shifted up because that intercept is going to be the 1 over Vmax. And if this is going to be smaller, this is going to be bigger. When it comes to measuring the kind of effectiveness of an inhibitor, we often talk about a couple terms, Ki and IC50. So basically your Ki, that's your dissociation constant for your inhibitor, kind of like how we had a Kd when we did binding thermodynamics, and kind of similar to Km, how that was measuring affinity for the substrate. The Ki is going to be measuring in affinity for the inhibitor. The stronger the inhibitor binds, then the lower the KEI. We can talk in terms of the response as well. So we have this term called the IC50, and the IC50 is going to be the concentration of the inhibitor at which you reduce the enzyme's activity by half. So to summarize, competitive, you're competing for the substrate, but can fall out and let substrate bind. Non-competitive, you bind to E or you ES, and uncompetitive, you bind to ES, but not E. With a competitive inhibitor, you reach the same Vmax because if you add enough of the legit substrate to outcompete all the fakes, the enzymes don't act normal. But you have an increased apparent Km because substrate gets diluted by the competitor and becomes harder to find. But we can basically switch the scenario and compete out the inhibitor to make the inhibitor harder to find. In the case of our non-competitive, well, we're going to have a decrease in our Vmax because not all the substrate-bound enzyme is actually able to do its job. But we're not going to have a change in our parent Km because the competitor binds to a different location, doesn't affect the enzyme substrate binding, isn't competing. With our uncompetitive, well, here, not all the substrate-bound enzyme is actually able to do its job, so we're going to get a decrease in our Vmax. But because the enzyme substrate complexes become like stabilized, even though they're useless, you're going to get a decrease to parent Km. And then remember, we have our irreversible covalent inhibitors, where they're going to bind and basically trick the enzyme into thinking that they're substrate and attacking it. So this is typically when we have one of those mechanisms where the enzyme is actually forming a covalent link. So it has a covalent catalysis mechanism, and therefore it normally forms a temporary link with the substrate. But in this case, it's going to form a permanent link with the inhibitor because basically the inhibitor is going to be a worse leaving group. And so it's going to get stuck on there, preventing the enzyme from regenerating. And a classic example of that is going to be your ampicillin and your other beta-lactam antibiotics.